We are beginning our afternoon session, and I'm pleased to let you know that we have a representative of the generation of the great-grandchildren of Yuval, and Professor Misha Smolkin from the Hebrew University will tell us something very interesting. Those of you who are professional physicists know that there is a theorem which says that you cannot break spontaneously a continuous symmetry in 2 + 1 dimensions. And Misha will show us an example where this theorem is bypassed.
Well, almost true.
Almost, yeah.
Of course, it's hard to bypass theorems.
Yeah, of course. It all depends on the assumption.
That's true. Yes, and this theorem has to do with finite temperature also, right? So, let me first of all begin by expressing gratitude to the organizers of this event for inviting me to celebrate anniversary of one of Israel's most prominent researchers. It is certainly a great honor for me to be part of this event. And before I forget, I wanted to draw your attention that this year is also anniversary of the Hebrew University. So Yuval and Hebrew University were born in the same year. And unfortunately, I can't compete with Eliezer, so I will not tell you the story. And it's true that I never met Yuval in person and never talked to him. But I think this topic would entertain him, so this is why I prepared a short remark. So this is my remark. So given Yuval's deep interest in symmetries, we already heard about it today, which culminated in his independent and leading role in the classification of hadrons. I chose this topic in the hope that it might have entertained him had he been in the audience today. So let me describe a little bit, some short introduction. Well, actually, the whole talk is very elementary. So this is a short introduction. So we tend to associate greater order with lower temperatures. Okay. In other words, temperature is somehow not a big friend of order. So this intuition comes from our experience with all kinds of structured phases and condensates, such as crystals, of course, superconductants, magnets, electroweak symmetry breaking, etc. So here is a simple visualization of this idea. So we have a nice two-dimensional lattice at low temperature. So this is blue lattice. Temperature is low, so thermal fluctuations are quite suppressed. So basically, there are almost no thermal vibrations. So it is ordered, so the symmetry is quite limited. You can shift it by certain shifts, and you can rotate by certain angles. Then you turn on temperature, so it gets hotter. So the vibrations increase. So the lattice, the atoms start walking towards their neighbors. So in other words, they travel to adjacent cells. And eventually, at some point, they are so confused, they don't know which one of do they belong to this cell or to that cell. So this is the picture. So it's quite disordered. And now it is more or less symmetric under any shift and any rotation. So symmetry certainly increased as we increased temperature. So, and this is why we have this commonly held view. So although symmetries can be broken, in the absence of thermal fluctuations, they are always restored in thermal states at sufficiently high temperature. So this is a kind of perception, wide perception. And this idea is largely supported by this nice thermodynamic potential, free energy. At finite temperature, we minimize free energy. So you have certain temperature and certain energy. You your system wants to occupy state with highest entropy. And these states are usually disordered states. But I want to also remind you that although symmetry restoration at high temperatures is commonly observed, it is not a fundamental law of thermodynamics. So there is no thermodynamic law like that. And exceptions do exist. So there is no really theorem here. And what are exceptions? So this is probably one of the well-known examples because it is taken from the textbook by Landau Lipschitz on statistical physics. So it's real. So these are the crystals. They're real. This is a chemical formula. So here it is, taken from Wikipedia. So this so-called Rochelle salt, this crystal has two Curie temperatures, 18 degrees and 24, minus 18 and 24 degrees. So below this first Curie temperature, the symmetry structure of the crystal is richer than the symmetry of the crystal in between two Curie temperatures. Okay? So the crystal exhibits lower symmetry at intermediate temperatures here. In other words, you start heating it, and above first Curie temperature, you get lower symmetry. Now, another example that was constructed in the 70s by Steven Weinberg, it's a quantum field theory example. I do not present formula here of this example, but it's very simple. Just two scalar field theories, two massive scalar field theories, coupled through phi to the 4 interaction. Okay, so these two massive field theories. Each field belongs to ON group. So what happened? So what Weinberg showed in his paper is that. So again, this model is in 4 dimensions. So what he showed is that once you raise temperature in this model, in the specific model, one of the ONs, one of the symmetries breaks, or two of them, and therefore, he showed that this phenomena holds to all orders in the weak coupling. So again, this example belongs to intermediate regime, so for intermediate temperatures, because again, phi to the 4 theory in 4 dimensions is not UV complete, so at certain point, your temperature is so high, you hit Landau pole, or for those who are not experts, it means that your theory loses any predictability, so it just makes no sense. Everything is, coupling is infinite, and therefore you have to substitute it with something else, complete UV completion, and and who knows what happens above this temperature. So therefore, it's natural to raise the following question: can symmetry remain broken at all temperatures? So this is a so-called persistent symmetry breaking. Is it possible? So I was told once that when you ask this question in science, so the answer is immediately no. If there is something in the title like that, so the answer is no. So this is a counterexample here, because eventually the answer will be affirmative. Okay, so it will be true. So there are examples like that, and this is what I'm going to do in the remainder of my talk. So I will review selected, because, I don't have that much time, so I will review selected recent results and discuss ongoing research in this direction. So let me start from first example, 5 years old example. So this was done in collaboration with the organizer, Eliezer, Zor Komargotsky, Chanha, Shumyadip Chaduri, and Noam Hai. So this is the Hamiltonian of the model. So again, this is the free part, and then phi to the 4 interaction. So there are two fields, phi 1 and phi 2. Phi 1 belongs to ON, so it is symmetric. It's a vector field, scalar vector field. And phi 2 transforms under Z2. So in other words, it's just like ordinary Ising model. So it is symmetric under phi 2 goes to minus phi 2. You can see it explicitly because you have only even powers of field. So as it follows from the title, we consider it below 4 dimensions. So mostly, of course, below 4 dimensions, there are, well, the most interesting, of course, dimension is 3, 2 plus 1. But again, you can consider it in any dimension between 3 and 4, obviously. And in fact, of course, the most interesting theory is in 3 dimensions, but unfortunately in 3 dimensions, it's a 5 to the 4 theory, it will be strongly coupled. So it's hard to analyze it analytically. So therefore, again, here I forgot to mention that in 4D, this model is a kind of trivial. It is free in the IR. The only fixed point in 4 dimensions is just a Gaussian fixed point. And it has the same pathology as 5 to the 4. It is not UV complete. You hit one dipole at some point. So, but below 4 dimensions, this model has interacting Wilson-Fisher fixed points. Again, in the case of just a single field, you have one Wilson-Fisher fixed point. So here you have more couplings, 3. Okay, so you have phi 1 to the 4, phi 2 to the 4, and phi 1 square, phi 2 square. So you have 3 couplings, and therefore you have more possibilities. You have many fixed points. And we are interested in these theories that you get once you reside in one of the fixed points, because at the fixed point, the theory is conformal. And what is special about conformal field theories, this is the answer to this question, they are UV complete because they look the same at all scales. So there are no pathologies. Furthermore, any field theory that is well defined in the UV generically flows to a fixed point, some UV conformal CFT. Conformal fixed point in the UV, so UV CFT. So this is why we focus on CFTs, because on the one hand side, they are simple, they are UV complete, and they basically correspond to UV end of any asymptotically safe QFT. So direct analysis, as I said, direct analysis of this theory in 3 dimensions is quite challenging because, again, the theory is strongly coupled. Well, we don't have that many tools to address strongly coupled systems. However, you can employ either the standard epsilon expansion or large N techniques. So this is a way to attack or to just analyze this model analytically. So this is what we did, and these are the results. Okay, these are the results. If you take n strictly infinity, so large n here means strictly infinity at this point. I will comment about finite n in a moment. So if you take n strictly infinity, then you get all kinds of features. So what are the features? First of all, RG flow equations simplify, and you find a line of fixed points. Rather than isolated fixed points, you get a line of fixed points. So the technical term for the line of fixed points is conformal manifold, so parameterized in a certain way. So you get conformal manifold. In addition, for any choice of a point on this line, you get a modular space of vacuum. So in other words, your potential has a value. So at 0 temperature, this value is just a straight line, okay, straight line like that. So this is just phi 2 square and phi 1 square as indicated on the axis. So at the origin, both phi 1 and phi 2 vanish. So this is a symmetric phase and it's a CFT. Okay. If you go away, so if you just travel along the valley, you pick here any point, then you break the symmetries, of course, both conformal symmetry and ON cross Z2. Now, at finite temperature, now you can analyze. You can keep n infinite and analyze what happens at finite temperature. So at finite temperature, this line is deformed away from the origin. Okay, so you get this line. You still have a valley of vacuum, which is quite surprising, but this is just a result of the calculation. Of course, unfortunately, or fortunately, it depends on your standards. Once you turn on 1/n corrections, what happens in this model is that all these features disappear. Okay, they are gone. So in particular, at t equals 0, this line disappears, and you just stay with one vacuum, just a symmetric CFT. Now, this line also goes away. Okay, so but it doesn't matter which one of these vacua survives, it will always break symmetry. So in other words, using this large N, you can immediately see that the symmetry will be broken here. And I tell you which one of the symmetries breaks. Basically, the true vacuum is here on the phi2 square axis. Phi2 corresponds to Z2. And once you introduce 1 over n corrections, you have a symmetric conformal field theory at 0 temperature, and a theory, once you raise temperature, you take this symmetric CFT, you raise temperature, and Z2 breaks. Now, furthermore, you can actually find this critical value of n, how large n should be to hit this broken phase, and it happens to be of order 17. So if you go to values n larger than 17, then symmetry, Z2 symmetry is always broken at finite temperature. So now, of course, there are a number of weaknesses at this point. So one weakness is quite obvious. So analytical results are reliable only for small epsilon. Again, those students or non-experts, epsilon is a measure how far you sit from 4 dimensions. So if epsilon is small, you are close to 4 dimensions. If epsilon is 1, you are sitting in 3 dimensions. The analytical calculation can be done when you are close to 4 dimensions. And then the question whether all these results survive as you take epsilon to 1 when you go down to 3 dimensions. So this is one of the weaknesses. So you don't know. In principle, if you are picky, you can say, well, who knows, maybe just an artifact of epsilon expansion. So persistent breaking of Z2 in 3D remains uncertain within this approach, if you are picky. Now, in principle, you can deal with this weakness by if you abandon locality. So if you abandon locality, we replace this local kinetic term with non-local. This is the so-called generalized free field. It is still Gaussian, quadratic in phi, but it is not local anymore. So you just replace it with non-local theories. So non-local theories in condensed matter context, non-local theories like that describe long-range Ising models, for example. So if you do it, just if you wish for academic purpose, if you do it, you can remain in 3 dimensions. You see here it's already 3. You can just sit directly in 3 dimensions and fine-tune this delta. This delta is also corresponds to the scaling dimension of phi. You can tune this delta to a special value which is close to 3/4, okay, up to epsilon. You can tune it close to 3/4, then this phi to the 4 interaction becomes weakly relevant in analogy to what happens with the ordinary phi to the 4 close to 4 dimensions. So in other words, you just substitute epsilon that measures how far you're from 4 dimensions with epsilon that measures how far you're from 3/4. Or if you wish to go to local theory, you have to take epsilon to be 1 here. Okay, so then you can analyze this model directly in 3 dimensions, and all the features and symmetry breaking patterns valid also for this model. So it also happens here. But again, what is the weakness? The theory is non-local, obviously. So whether it's a sign for being worried, I don't think so, because recently these weaknesses were completely removed. So let me mention 2 recent results. So one result was achieved by this group of people, Bilal Avashan, Rong, and Michael Scherer. So they basically took this model directly in 3D and used the so-called functional renormalization group methods, FRG methods. It's just a powerful tool to analyze RG flow in field theory. And well, solved this exact FRG equations in 3 dimensions, directly in 3 dimensions, and confirmed that this theory exhibits persistent symmetry breaking of Z2. So again, now it's a local, it's directly in 3 dimensions, and they just fully analyzed it using PSB. So of course, at some point you have to use numerics, so they use numerical methods, and they showed that it works. So PSB happens here indeed. Shortly after this paper appeared another paper by Zohar Komargotsky and Fyodor Popov, so where they constructed another example of a local analytically tractable 3D CFT exhibiting PSB. So, well, let me just briefly mention how it looks like. Again, the model has ON cross Z2 symmetry. It is built from the critical ON. So this is critical ON. So you take phi to the 4 theory with ON symmetry. You consider large N limit. You can rewrite it in this way. So this is critical ON model. This is free field theory. So this free field theory is certainly symmetric under Z2, and this model is symmetric under ON. Phi 1 is vector here. So you start from this CFT, decoupled free field and critical ON. Now the critical ON has interesting field sigma, okay, also known as Hubbard-Stratonovich field. So this field sigma, its scaling dimension is 2 up to 1 over n corrections. So if you include 1 over n corrections, the scaling dimension of sigma becomes slightly below 2. And in particular, again, sorry, this is for those who are experts. So the scaling dimension of this operator, sigma, is slightly below 2, phi 2 square, it's free field, so it's 1. So the scaling dimension of this operator is slightly below 3. This is exactly like in phi to the 4 theory in 4 dimensions when you go slightly below 4. So they studied this model, analyzed it analytically. Again, there are all kinds of interesting subtleties there. So they analyzed it and found that this model exhibits persistent symmetry breaking of Z2. So the upshot, this is the upshot. So local unitary UV complete relativistic QFTs, which exhibit symmetry non-restoration at all temperatures, do exist. Now, this raises 3 natural questions. I have only 5 minutes. So therefore, I relegate these two to the summary, and I will only address one of them. So what is the mechanism behind PSB, or why does this counterintuitive behavior occur? Are there examples in 4D, and what are the potential applications of this phenomenon? So let me do it quickly. So this is the intuitive picture for this persistent symmetry breaking. You have this ON rank, ON group, large group, and you have this small group, Z2. This ON group, you can think about it as N is large, so it's like heat bus. Heat bus, and the Z2 is small. It's a very, it's a subsystem. So what happens is that the symmetry of a subsystem breaks, but the entropy of the whole system goes up because the heat bus compensates, and eventually the entropy increases, even though the subsystem resides in a broken phase. So while helpful, this intuition helpful, it does not really explain the occurrence of PSB. And let me just briefly mention this, the following model here that I study with my student Lev Jung and Michael Scherer and Havashin. So this is the model. You take this model that exhibits Z2 breaking. This is a scalar model that I introduced. And you add free fermion. This is Dirac fermion coupled through Yukawa interaction to this model. So again, this model is strongly coupled in 3 dimensions, but you can do again epsilon expansion, for instance. And if you do it in, and this Z2 now is promoted to parity. Sorry, I'm in a rush to finish. So this Z2 is now promoted to parity. Why it is promoted to parity? Recall that phi 2 transforms under Z2. Phi 2 goes to minus phi 2. So you can think about it as pseudo-scalar. So in 3 dimensions, mass operator, psi bar psi also flips sign under parity. So therefore, if you think about Z2 as parity, this interaction is symmetric. So this model respects ON cross parity. And now you can check what happens with it if you raise temperatures. Well, first of all, you have to identify fixed points. It's hard, it's strongly coupled. You can do epsilon expansion and check what happens then at finer temperature. So in 3 dimensions, it's hard. So you have to do use all kind of other methods. But you can do, again, epsilon expansion. And this is what we find, that parity breaks in this relatively narrow window of n's. So in particular, it's a bit opposite to this intuition, because you would think that if n is already large enough, you should continue. So it should continue. The symmetry should be broken 1 minute, but it does not happen. And so these are just facts. So let me switch to summary and discussion. 4D examples. So there are examples in the literature. Eliezer is author of one of these papers. However, these examples were analyzed in the case of infinitely many fields. So it would be interesting to see what happens with 1/n correction. A fully fledged, if you wish, 4-dimensional example was not worked out yet. So in all existing examples, n is large. So other models with n of order 1. So that would be interesting to understand, because then it will become more realistic. Now, what about applications? So there are recent discussions in the literature about high temperature superconductivity, because, well, if you think about superconductivity as, again, in this context of phase transition, so then again, it's a low temperature phenomena, but if you can somehow cook this PSB, appropriate PSB, maybe you can get superconducting phase at high temperatures. And there are models that were recently proposed in the literature. So what about application of breaking of parity? So we call it thermally induced quantum Hall effect, because if you start at 0 temperature and parity, if the system is parity symmetric, then you do not have whole conductivity. But if it breaks at finer temperature, this whole conductivity will emerge. And it would be interesting to verify it explicitly. So thank you.
Thank you very much, Misha. I allow myself to ask a question. How do you see? To describe high TC superconductivity, why does it have to be UV complete?
No, that's not the whole.
Does it have to be persistent?
That's true. That's true. I'm just saying that if there are examples where, in field theory, where the symmetry breaking pattern is opposite to what we are used to, then in principle you can. That's the point. Persistent. I agree that you do not really need persistent superconductivity. You need it just at intermediate temperatures would be enough. Yes.
You haven't told us how exactly you incorporate temperature in these quantum field theories. My question is, what happens to this PSB if you discuss hydro systems? Do you have an example of hydrodynamics where you go to very high temperature and temperature there is a field, and you can show that there is a restoration of.
So first of all, let me answer a simple question. Hard question I will try to avoid. So simple question: how we incorporate temperature in the standard way. You have field theory. You put it on a circle, right? So on a circle, on a cylinder, and you just do calculation. You basically calculate free energy. So in this case, of course, at 0 temperature, well, you have basically a standard conformal potential. And then when you turn on temperature, there are thermally induced masses. So you just calculate the thermally induced masses and you check whether they are positive or negative to understand, to analyze stability of the symmetric vacuum. So this is what we do. Indeed, I skipped it because, in half an hour, it's too much to present all kind of technical details. Now, about hydro, no comments.
Thank you very much.
Okay.